the organizers for organizing this whole conference, and also thanks to Noel and also Isaac for being great and workshopping my talk and being extremely helpful. Okay, so first of all, just a quick outline of what I'm going to talk about. I'm going to give just the basic definitions. What is a Coxeter group? What do I mean when I say a random Coxeter group has some property? And then I'm going to tell you a couple of properties that I have some results about. So one of them is the homology of the nerve. I'm going to tell you what that is, and the other one is hyperbolicity, which you've heard defined a few times, but I'm going to remind you what it is as well. Okay, so first of all, just what is a Coxeter group? So throughout gamma is going to be a graph, finite number of vertices. The edges are labeled with integers at least 2. If there are any, there probably aren't any combinatorists in the audience, but if there are any combinatorists, when I say labels, I mean weights. Sorry, that's how we do things in Coxeter groups. The point to that is just that you can have the same label more than once. If you weren't worried about that, don't worry about it. So given such a graph, you have the associated Coxeter group. So the graph is giving a presentation for the group. The vertices of the graph are going to be the generators of the group. Each generator is going to have order 2. And the labels on the edges are just telling you what the relation should be between those 2 generators. So if the label between 2 vertices is m, then you take the first one times the second one to the m. That should be 1. And that's your relation. So also, just for convenience, sometimes if an edge doesn't appear in the graph, I'm going to say that it's labeled infinity. So when I talk about edges labeled like 2, 3, and infinity, I mean edges labeled 2 and 3 and non-edges, like edges that aren't in the graph. Also, if all edges are labeled 2 or infinity, the group is called a right-angled Coxeter group. And that, in that case, you can kind of forget about the labels, right? Because either you have an edge and it's labeled 2, or you don't have an edge and it's labeled infinity. So it's just whether or not you have an edge. And yeah, so just a couple examples. A lot of groups that you know in log are actually Coxeter groups. So if you just have 2 vertices, no edge between them, so that's I could have also drawn that in and had it be labeled infinity. There's no edge there. That's just a free product of the mod 2s. If you have those same 2 vertices and you have an edge labeled m in between them, that's just going to give you the dihedral group with 2 m elements. And then if you have a triangle like this, that's labeled 3, 3, 2. Actually, so it turns out that's going to give you S3, the symmetric group. And actually, in general, if you have like a line of n vertices with the edges on the line are all labeled 3 and all the other edges are labeled 2, that's going to give you the symmetric group on n things. So you are secretly familiar with Coxeter groups, even if you're not familiar with Coxeter groups. All right, so what do I mean when I say that a random Coxeter group has some property? So first of all, we choose a random Coxeter group on n vertices. So you take your n vertices, you independently think about each pair of vertices, and you're like, okay, well, what edge should appear here? So I'm going to have some probability that there's going to be an edge labeled 2, and some probability that there's going to be an edge labeled 3, and 4, and 5, and so on. And those probabilities should all add up to less than or equal to 1. And the reason it's less than or equal to 1 and not strictly equal to 1 is because there's some probability that there's just not going to be an edge there at all. Right, so we'll define p sub infinity. So P2 is the probability that the edge is going to be there labeled 2, P3 is the probability that the edge is going to be there labeled 3, P infinity is just 1 minus the sum of all those, which is the probability that there's just not an edge there at all. So, quick example of how this goes. It's kind of hard to give an example of a random Coxeter group, but so let's say n equals 3, so we have 3 generators. And let's say, so we've got P2 is a half, P3 is a quarter, P infinity is a quarter, and we're just going to say everything else is 0. So I'm gonna think about rolling my 4-sided die, and if I get 1 or 2, I'm gonna label the edge 2. If I get a 3, I'm gonna label it 3, and if I get a 4, it's gonna be labeled infinity or just not there. So, okay, I'm rolling my imaginary die. Let's say the first I'm thinking about these 2 vertices. Rolling my imaginary die. Let's say it came out with 3. So that means I'm gonna draw that edge and label it 3. Now, okay, let's think about these 2 vertices, rolling my imaginary die again, maybe this time it comes up 4. Okay, so that's an infinity, so that means that edge isn't going to be there. So I'll maybe draw it with a dotted line just to indicate that I thought about it, but it's labeled infinity, it's not actually in the graph. And now finally I'll roll my die again. Maybe this time I got a 1, and so I'm going to put, for the last edge, I'm going to put that in and that would be labeled 2. All right, so this is kind of how we're thinking about picking a random Coxeter group. And then what does it mean to say that a random Coxeter group, there we go. What does it mean to say that a random Coxeter group has some property? Question?
Why don't you ever label something with a 1?
Good question. So, yeah, so the relation that you get when you have an edge labeled M is that vi bj to the m equals 1. So if m was 1, that would just be vi bj equals 1. But each generator is its own inverse. So, so then you really kind of have the same generator more than once. Other questions? Okay. So what does it mean to say that a random Coxeter group has some property? We want to kind of know what properties of random Coxeter groups might be because, we sort of want to know what kinds of properties are common in this space of Coxeter groups. So we kind of want to, the point of studying random Coxeter groups is sort of to cut up the space of Coxeter groups in a way that we can say, okay, well, these ones over here have this property, and these ones over here have this other property, and so on. But what does it mean to say that a random Coxeter group has a property, right? So, so the thing we're going to be interested in for this is we want to know what properties random Coxeter groups asymptotically almost surely have. And that just means, so we pick our random Coxeter group on n vertices. And these probabilities are depending on n, right? So as n increases by probabilities of having different labels can drop or increase or whatever usually drop. So we have the probability that a random Coxeter group on n vertices has some property. We just want to let the number of generators grow to infinity and see, okay, well, what kind of happens in the limit? Does the group have this property with probability 1 as n goes to infinity? Okay. And so actually, if you're familiar at all with random graphs where you've seen results about random right-angle Coxeter groups, if the probability that any label besides 2 or infinity appears is just 0, this is just the usual standard Erdős-Renyi model for random graphs, which is what's basically always used to study random right-angle Coxeter groups. And that's that's kind of nice because there's this whole theory of random graphs where you can just pull results from, and people have found that to be very useful. It does not exist for random edge-labeled graphs, unfortunately. Well, fortunately, because that's why I have a job. But okay, so the first property that we're going to talk about is the homology of the nerve. So what is the nerve? So the nerve is just this simplicial complex associated with the Coxeter group. The subsets are going to be the subsets of the generators that generate a finite Coxeter group. So first of all, the vertices are going to be the same as the vertices of the graph. And any edge that appears in the graph, no matter what the label is, any edge that actually appears without labeled infinity is going to appear in this simplicial complex. And then for larger subsets, you need to know whether or not that subset generates a finite Coxeter group. But the finite Coxeter groups are well understood. There's this list that you take your graph and you're like, okay, is it on this list? If it's on this list, it's finite. If it's not, then it's not. So this is not a hard thing to figure out what the nerve is. And it turns out this is a result of Mike Davis. So if we know the homology of the nerve and some other information that I'm going to kind of sweep under the rug here, we can actually compute the cohomology of the group, which is cool because that's hard to do in general. So it would be interesting to know what the homology of a random Coxeter group is. So for a right-angle Coxeter group, the nerve is actually just the Quique complex on gamma. So you look at your graph, you look at every subset of the vertices, you're like, okay, is this a Quique? Is it a complete subset of the graph? And if it is, then it generates a product of Z mod 2s, that's finite. If it's not, there's some edge labeled infinity, and that's going to give you an infinite order element, and so it's going to be infinite. And so, so let me give you an example and then tell you why that's relevant. So here's an example of how you get the nerve from the graph. So I've got this graph over here. The vertices are the same. You can see the edges. I've colored them so you can see where the edges match up. And if you look at any set of 3 of these vertices, that's always going to be a triangle with edges labeled 3, 3, 2. That's a finite Coxeter group, and so the faces of this tetrahedron are all filled in. But if you take this whole thing, this square of 3's with 2's on the diagonals, that's an infinite Coxeter group, and so the middle of this tetrahedron is not filled in. Okay? All right, so So again, for a right angle coxeter group, the nerve is just the Puig complex. Matt Hale has some work on random Puig complexes, which Meg Davis and Matt Hale put together to get this result, to actually compute the cohomology of a random right angle coxeter group. So it turns out, basically, if you have sort of just the right number of edges, you have, so the way we're going to read things like this, or if you have some, p2 times n going to infinity, that means we have a lot of 2's. So in the right angle case, that just means we have a lot of edges because all the edges are labeled 2. So we have a lot of edges, but now we've got p2 to the k plus 1 times n going to 0. So we've got, so somehow we have not, we've got a p2 times n going to 0, so this is like, we have not too many edges. So we have enough edges, but not too many. We'll get this one dimension in which we have non-trivial cohomology, and everywhere else it's going to be trivial. So, so the question is, okay, well, can we extend this result to the general setting? And the current status of that is I do not have a full extension of this result to the general setting, but I do have some information about the homology of the nerve, which is sort of the first step towards this. Okay, so first of all, I know sometimes when the homology of the nerve is trivial. This is not all of what I think is true, but this is all of what I have proved for the trivial part. So, so for this, we're not going to care much about what our edges are labeled as long as they're bigger than 3, just because you need a lot of 2's to have a finite coxeter group, and so if you don't have enough 2's, you're just not going to see things that are going to that are going to contribute to the nerve at all. So, so this is just saying, okay, well, if I have not too many 2's, right? I've got something with a p2 that's going to 0. I have not too many 2's. And the ratio of big things to 2's is also not going to infinity, so I don't have too many big things in relation to the number of 2's I have. Then just the dimension of my nerve isn't going to be big enough to see non-trivial homology in dimension higher than k plus 1. So, so if you don't have a lot of 2's and you don't have too many bigger labels, the nerve is going to have small dimension, and you're not going to see homology in large dimension. Sort of the more interesting part of this theorem is when you have non-trivial homology. So, all right, so this is, I've got something with a 2 that's going to infinity, so I need to have a lot of 2's. I've got something with a 3 that's not going to 0, so I need to have a lot of 3's. But now I've got this 1 minus t infinity, so that's just the probability of having any edge at all. And that needs to be going to 0. So somehow I need to have a lot of 2's and a lot of 3's, but not too much of anything overall. So there's a little bit of a tension there, but if I can strike that balance just right, and yes, this is possible to do, I checked very carefully, then you're going to see non-trivial homology in that dimension. And just so, yeah, I mean, the reason you need this condition are basically, so the way the proof sort of goes, I'm not going to, like, very broadly, is, so I'm looking for a thing, some subgraph in the graph that's like sitting in there in the right way to actually produce non-trivial homology in the nerve, and that graph has 2's and 3's. And if I have too many edges, that can mess up the way that it sits in there. So that's why those conditions are relevant. Okay, so that's this is what I have about homology. I'm going to totally switch gears now and talk about hyperbolicity. So if you don't care at all about homology and you care a lot about hyperbolicity, this is a good time to start paying more attention. All right, so you've seen this definition a few times already, but just to remind, well, you've seen this definition once in a couple other equivalent definitions. So a metric space is delta hyperbolic if all of its geodesic triangles are delta stem. So in the sense that, if you take a delta neighborhood around any 2 edges of your triangle, the third edge should be entirely contained within that. And it's, we say it's hyperbolic if it's delta hyperbolic for some delta, and a group is hyperbolic if its Cayley graph is. And if that's true for one Cayley graph, it's going to be true for every Cayley graph with finite generating set. Okay, so for coxeter groups, this is actually, you might think that it's like, yeah, so I don't know. You might or might not think that hyperbolicity would be a hard thing to tell whether a group has or not. For coxeter groups, this is actually easy thanks to Mousson. So a theorem of Mousson says that basically you can look at the graph, right? And so, I mean, even if you don't even know what hyperbolicity is, really, you can do this pretty easily. So you look at the graph, you look at every subset of the vertices, every subgraph of the graph. So there are 2 bad things that could happen that could cause your group to not be hyperbolic. One is that some subset could to be on at least 3 vertices in generator that you put in your reflection group. If this is another, there's a list of these. You take your subgraph, you compare it to this list. If it's on the list, then that's a bad subgraph and your group is not hyperbolic. If all of your subgraphs are not on this list, you're okay so far. You also can't have anything that generates a direct product of infinite subgroups. So you look at your graph, you find all of the anything that generates a direct product, so that's any two subgraphs, or any two sets of vertices where all of the edges between them are labeled 2, is going to give you a direct product. And if you ever find one of those where both halves give you an infinite subgroup, so they're not on this list of the finite ones, then that's also bad. So if you have any of these bad subgraphs, then your group is not going to be hyperbolic. If you don't have any, then your group is going to be hyperbolic. So figuring out when a random Coxeter group does or doesn't have this hyperbolicity property is just a matter of figuring out when it does or doesn't have things from this list of bad subgraphs. So and basically this just says, so if I don't have too many 2s or 3s or 4s or 6s, then my group is going to be hyperbolic because I'm not going to see anything from this list of bad subgraphs because they all have 2s and 3s and 4s and 6s. Or some combination thereof. And the thing you would sort of like to be true, the nicest sort of random result is when you can kind of say, okay, well, if I have all of these things, then this asymptotically almost surely is true, and if I reverse any one of those, then it asymptotically almost surely isn't true. And that's not quite what I have, but I have something like that. So if I have too many 2s, and also there's an issue with how many infinities I have. I need to not have, I need to have some of those too. If I have or if I have too many 3s, or if I have too many 4s and also I need too many 2s, or if I have too many 6s, but then I also need too many 3s and 2s. So in any one of these 4 cases, then the graph is asymptotically almost surely going to contain one of these bad subgraphs, and the group is asymptotically almost surely not going to be hyperbolic. So other things I thought about, other things I'm thinking about, future directions. So I'm not going to really tell you what any of these things mean, but so I also have results on when a random Coxeter group is FC type, if you know what that is. So if you're interested in that, that's in my paper, that's on the archive. You can Google random Coxeter group, the first thing that comes up. Things I'm currently thinking about or thinking about in the future are, so also not going to tell you what this means, but so Coxeter groups are either thick or relatively hyperbolic, and I'm trying to figure out when random ones are one or the other of those. There's more to do on the cohomology thing, right? I have some information about the homology of the nerve. I know something about when it's non-trivial, and I know when it's trivial in large dimension. There should also be conditions under which it's trivial in small dimension, first of all. And second of all, there's the rest of the work that's needed to do to come up with the actual theorem about the cohomology. So there's still a lot more to do there. Any other property you can think of is open, and I'm not thinking about it, and I don't know anybody else who is. So, advertisement for this. Thank you.
Are there any questions for our speaker?
Can you give any intuition as to why to detect hyperbolicity we only need to think about edges labeled 2, 3, 4, and 6?
Yeah. Well, so I mean, I don't know if this is much of an intuition, but just Musang's criterion for this, it basically, So the reason 2s are maybe an intuitive reason of why 2s are important is if you see a lot of 2s, you're going to start seeing more direct products of things because you're going to, and so a direct product of, if you see a direct product of infinite subgroups, that's going to give you a flat, which is not, and also if you have something that generates a Euclidean reflection group, just if you look at the list of these, they have 2s, 3s, and 4s, and 6s, and if you have something like that, that's kind of also going to give you a flat.
So you said something about hanging enough edges, but not too many. I don't know if I just too many.
Yeah. So let's see. I think this is probably what the slide that I said that on. So, yeah, so enough edges means that, so the probability, okay, so when I say enough edges, I mean that an edge is sufficiently probable. So it's probable enough that if you take the probability of an edge appearing, you raise it to the k, you multiply by n, you let that go to, you let n go to infinity, you have enough that that is still going to go to infinity, so that multiplying by k times by whatever your function for P2 is not enough to cause that to not go to infinity. But if you multiply by one more instance of P2, then suddenly it's going to 0. So there's like, so the thing that's on the board is exactly what I meant when I said that.
Could you give a flavor for how to prove the listening random?
Oh, okay. Yeah. So proving hyperbolic is sort of the easy direction because it's kind of easier to. So proving that it is hyperbolic is sort of easier because it's easier to show that your graph does not contain a subgraph. So I mean basically the idea is. This is going to take too much time to do properly, but basically if you compute the expected number of subgraphs of, whatever subgraph you're trying to rule out, you compute the expected number that's going to appear in the graph of those. And if that's going to 0, then the probability that there is one at all is also going to 0. Showing that a subgraph does exist is kind of harder because it's not enough to show that the expected number doesn't go to 0. You have to, there's a summation with the variance, but.
Do you think you'll be able to extend the scope to kind of non-positive curvature setting?
I don't know. I don't think it would be like, it wouldn't really, well, Cox figure 0 is at 0, so I'm not sure. So,
Oh, I see. The finding for the positive curve.
Yeah.
All right, let's thank the speaker again.